Welcome and thank you for staying by. At this time, all participants are in a listening mode until the question and answer session at today's conference. At that time, you may press star 1 on your phone to ask a question. I'd like to inform all parties, if you have any questions, I would like now to turn the conference over to Veronica McGregor. Thank you. You may begin.
Hi, good morning, and welcome to today's NISAR pre-launch teleconference. I'm Veronica McGregor with the news office at NASA's Jet Propulsion Laboratory, and I'll be your moderator today. NISAR is a joint mission by NASA and the Indian Space Research Organization, also known as ISRO, that will monitor Earth's dynamic surface. The full mission name is the NASA-ISRO Synthetic Aperture Radar, but we'll just refer to it as NISAR today. We're now 2 days away from launch, with launch being provided by ISRO at their Satish Dhawan Space Centre in Sriharikota, located on the southeast coast of India. NISAR team members from JPL and NASA are in India in anticipation of launch set for 8:07 a.m. Eastern Time, 5:07 a.m. Pacific Time on Wednesday, July 30th. They are joining us from India today to talk about the mission's important science, the collaboration between ISRO and NASA, and to provide details on the launch itself. Quickly, before I hand it over to the panelists, I want to remind members of the media on the phone line that you can ask a question by pressing star 1, and you'll be entered into the queue. For our other listeners who would like to submit a question, you can do it via social media by using the Ask NISAR hashtag. So that's hashtag Ask NISAR. Joining us today, we have Karen St. Germain, Director of Earth Science at NASA, Gerald Bawden, NISAR Program Scientist at NASA, Shanna McClain, Program Applications Lead for NISAR from NASA, Phil Barela, the NISAR Project Manager from JPL, and Marco Lavalle, the NISAR Deputy Project Scientist at JPL. And we really appreciate that they're joining us at 9:30 p.m. local time in India. It's a 12-and-a-half-hour time difference between us here in California, and we know that they've already had a very long day, but exciting day. As you can see, we did not have a representative from ISRO joining us on this call. They were, of course, welcomed and invited, but sent regrets due to their very busy pre-launch schedule and their deadlines as we get closer to launch day. And now I will turn it over to Karen St. Germain, the Director of Earth Science at NASA.
Good evening from India. It is great to be with you at such an exciting time. We are two nations with one mission. NISAR unites the U.S. and India to study our home planet together. NASA studies the Earth as a system. And as the first image is going to show you, today we have more than 24 missions in orbit studying our oceans, land, ice, atmosphere, and life on our planet. Yet we get a far greater understanding of how the Earth works when we look at the data from all of these missions together. Because together, we can observe how a change in one aspect of the Earth may drive change in others. Even small and subtle change can mean a significant difference across the entire Earth system. We are launching NISAR, the most sophisticated radar we've ever built. NASA undertakes this groundbreaking mission in partnership with ISRO. The science of NISAR will advance our understanding of the Earth system with cutting-edge technology capable of studying changes in land and ice, changes as small as a centimeter, in any weather and in both darkness and light. So why is this important? Let's roll the B-roll. Some change happens, this is important because we know that our planet's surface undergoes constant and meaningful change. Some change happens slowly. Some happens abruptly. Some changes are large, while some are subtle. With NISAR, we will see the precursors to natural hazards, such as earthquakes, landslides, and volcanoes. We'll see land subsidence and swelling, movement, deformation, and melting of mountain glaciers and ice sheets covering both Greenland and Antarctica. And of course, we'll see wildfires. We'll also see human-induced land changes, such as farm and ranch production, use of water for municipal drinking and farm irrigation, and infrastructure and land development, houses, commercial buildings, railroads, highways, and bridges. We will put NISAR science and observations to work, guiding and informing decisions so we can abundantly feed ourselves, safely build housing and transportation systems, and better prepare for and respond to natural hazards. I'm also really proud to highlight NISAR as a terrific example of NASA's unique end-to-end capability. From inventing new technologies to building missions, our science reveals the previously unseen, and we deliver those insights to help inform decisions. As an international partnership built on open science principles, NISAR is a model for the next generation of Earth observation capability. India built the spacecraft bus and the S-band radar and is providing the launch vehicle, launch services, and satellite mission operations. NASA's JPL built the L-band radar and the mission's radar reflector and boom. NASA is also providing a high-rate communication subsystem for science data, GPS receivers, a solid-state recorder, and the payload data subsystem. Finally, I want to recognize the leadership of ISRO and NASA's JPL team. Look, building a satellite on opposite sides of the world during a global pandemic was really hard, but it strengthened our relationship with ISRO. The collaboration, the cooperation, information sharing, and frankly, joint learning between our two agencies is a foundation that we look forward to continuing to build upon. Go NISAR. And now I'd like to introduce Gerald Bawden, NISAR Program Scientist from NASA headquarters. Gerald, over to you.
Thank you, Karen. Thank you so much. And it's exciting to be here in India on 2 days before we're launching. NISAR is going to be the first ever satellite to use two-of-a-kind radar that will operate together to study the Earth and our processes. NISAR is going to image the solid Earth, the living Earth, and the frozen Earth, and actually so much more than I have time to talk about here. So first, let's talk about the solid Earth. NISAR will measure changes in the land surface globally on average about once a week. The solid Earth covers earthquakes, volcanic unrest, landslides, land subsidence, any process that actually moves the land by either millimeters, we're talking sub-inch, out to kilometers, so we're dealing with miles. We'll be able to go ahead and track all these types of motions. Plate tectonics is responsible for shaping the Earth over eons, and these landscapes continue to change every day, but often imperceptible to the human eye. This is where NISAR comes in. NISAR will measure almost all the lands in the world, and will be able to go ahead and detect changes in positions less than a centimeter, less than a quarter of an inch. These changes could be associated with a fault, slowly accumulating stress before an earthquake, magma migrating from depths beneath a volcano that may or may not trigger an eruption, or landslides that begin to slip before a catastrophic failure. The animation that you see up on the screen right now is looking at Los Angeles in Southern California. You can actually see the colors where we rise up, where red is where it's up high, blue is where it's down low. It's rising and falling about up an inch and down another inch. So we've got 2 inches that it's moving up and down. This is all due to groundwater pumping. If you notice on the left side of the image right now, you got some black lines on there. These are faults. That's the Newport Inglewood Fault. And the deformation from groundwater pumping is actually concentrated on the faults. This could either mimic an earthquake, or it could also mask it, make it harder to understand if these faults are getting closer to failure. So NISAR is going to be able to help us do this, but globally in all different types of conditions. The living Earth. NISAR will measure nearly all the living Earth twice every 12 days. The living Earth are the plants, the crops, the forests, the lakes, the cities, the coastal regions. So if I could get the next image up. NISAR's 2 radars, the L-band provided by NASA and the S-band from ISRO, are excellent at measuring crops. The SR, it's a shorter wavelength and is able to really look at the growth of many crops like soybean, corn, and things along those lines. The L-band, the longer wavelength, is fantastic at looking at, I'll say, your tree crops or your almonds, and just looking at trees growth for forestry perspective, looking at tree inventories. And so the image that we're looking at on the screen is that in southern Florida, that's Lake Okeechobee. all the blue squares, this kind of quilt work, patchwork, things in there, those are all sugarcane fields. Each one of them is actually in a different stage of growth, different stage of being harvested, and the different color patterns that we see here are from NISAR-like data, from radar data, that we're able to look at and be able to actually begin estimating what will the crop production be for these types of crops. So this is just southern Florida. Take this worldwide. If we've got clouds in areas, we'll be able to actually penetrate through the clouds. The frozen Earth. We get the graphic up for Antarctica, that'd be wonderful. The frozen Earth are the glaciers, the ice sheets, the sea ice, the permafrost. NISAR will image nearly all of the Earth's frozen surfaces twice every 12 days. We'll be able to answer questions basically, how fast are the ice sheets moving? Are they advancing? Are they retreating? Will they be able to measure how much snow is being accumulated in some of the areas? This all provides vital information to the cryospheric community to better understand the complexities of these ice sheets. What we're looking up on the screen right now is an image of Antarctica. This was produced by scientists, and this took over 10 years to go ahead and generate this particular image. What you're looking at is actually rivers of ice. Just think of this as rivers, and the wider they get, so the blues and the magentas are rivers that are actually moving fast. This is ice that's being dumped into the ocean, and we're able to see exactly where it is, how fast they're moving. It took 10 years here. NISAR will be able to go ahead and produce this twice a month. And so we're going to be able to look at much subtler things than we've ever been able to do with NISAR. NISAR will be the most advanced radar system that NASA has put into space. And NASA actually has a long history of working with SAR. We actually launched the very first SAR satellite for civilian, for science and applications. The world ever saw back in 1978 was CSAT. Can you show the animation, please? The amount of data that NISAR is going to collect in the first year, we take a look at what's been collected in the universe, in the solar system. So this is NASA from Mercury to Pluto, and at the time here in 2017, 45 years of Landsat. NISAR is going to be 3 times that volume in the very first year. And so no other mission, Earth-observing mission, has collected as much data. The graphic that you're seeing up on the screen is actually showing simulated what NISAR's orbit's going to look like going around the Earth. And you can see we go from the South Pole to the North Pole, down South Pole. And when we talk about doing imaging the Earth twice every 12 days, it's either climbing, going from the South Pole to North, or back down. It's an incredible satellite that's got, will be just covering so much data. So NISAR is important for me. I'm responsible for all the science that comes out of NASA, so I'm obviously excited about everything that NISAR will be able to go ahead and produce. There are listeners on right now that don't yet realize how much of a game changer that NISAR is going to be for them. My hope is once people start using NISAR data, that they're not going to imagine time without NISAR being able to help address their issues and be able to help them out. We've produced a lot of different products, algorithms, computer programs and everything that's going to really help everybody do their science and be able to answer questions relevant to them. So NISAR, go NISAR. With that, I want to go ahead and hand things over to Dr. Shanna McClain.
Thank you very much, Gerald. So I'm going to talk now briefly about the applications of NISAR. From fire, flood, to food security, NISAR will help communities plan for and act on a range of critical decisions. For example, in January of this year, there were extensive fires across LA County, California. These are the Palisades and Eaton fires, impacting over 150,000 people, including many of our colleagues from the Jet Propulsion Lab and from our NISAR science team. With this image appearing on the screen, we can now see on the left the hyperspectral imagery from the AVRIS instrument that assesses the amount of hazardous char and ash remaining after the fires. And on the right, we have an AI-supported SAR-based Sentinel-1 image identifying the number of medical and health facilities impacted by the fire. By bringing these images together, we can have a narrative of both the health-related needs of the community and the available services in the area. With the NISAR mission, we can expect to see more improved damage assessments of critical infrastructure such as roads and energy grids, telecommunication lines, as well as homes and businesses. Beyond fires, NISAR will also provide crucial information on flood risk assessment and recovery. Just 3 weeks ago, extensive flash flooding impacted the Texas Hill Country, beginning the morning of July 4th. In the first few days of the floods, first responders were largely blind to the significant cloud cover that prevented the use of optical imagery and where no SAR passes were available. For this image that we currently see, in red we see the sheer intensity of rainfall in the area with the iMerge data. But to really understand what was happening on the ground, we were able to fly an airborne SAR-based asset referred to as UAV-SAR to provide information on the extent of the floods across the impacted regions. This is the image that we see now. The image we see here is actually the most representative of the type of imagery we can expect to see from NISAR. And while UAV-SAR provided critical information for supporting emergency responders, NISAR will also be a game changer for ensuring communities recover faster from floods by answering questions regarding how fast floodwaters will recede, whether there's damage to people's homes, and whether the roadways that take them home are accessible. Beyond disasters, NISAR provides a range of information, as previously mentioned, on ecosystems, the cryosphere, and food security. And for those working across the agricultural and land management sectors, NISAR's soil moisture products can aid in estimating crop production and health, and also support drought monitoring and assessment. The change detection capability of NISAR will also aid in understanding the extent of crops that are impacted by a range of hazards, including wind, tornadoes, and hail. Here we see optical imagery from Landsat 9 of the damage from wind and hail to croplands in Garden City, Kansas in 2023. Just imagine what NISAR will show us. And while NISAR will not predict fire, flood, or drought events, it will clearly address the needs for assessing risk to communities. It will also enable rapid recovery and put us on the path to strengthening our ability to build a more resilient future. So when I think about NISAR and why the mission is important to me, it's not just the range of societal benefits that it will be providing to communities around the world. It's also the fact that there are, once the data becomes available, there will be so many people looking to make the NISAR data very personal to them, to the stories of impact that they're experiencing. And so being able to see what opportunities and the range of novel applications that each one will bring to us is just thrilling. So I'll now turn things over to Phil Barela, the NISAR project manager.
Thank you, Shanna. I'm going to talk about NISAR's readiness to launch, and I'm very happy to say that we are ready to launch. And the launch is scheduled, as you heard, this Wednesday. We just got back from ISRO, having high-level meetings with ISRO and NASA, and both teams agreed that the spacecraft and the mission and the launch vehicle is ready to go. So everybody gave a thumbs up, and that's great news. The range looks good, weather looks good. It looks like the launch will happen this Wednesday, so we're very excited about that. If you queue up the photo there, I'll show you the status of where we were about a week ago. You see the spacecraft being encapsulated inside the fairing there on the left. If you see that black square in the front left of the spacecraft, that's one of the solar panels. You'll see the other solar panel, the tip of it on the other side. And then that cylindrical object in the top right on the spacecraft is the reflector. And you're going to see both of these deploy in just a minute here. It's very exciting. And then earlier this week, they rolled the spacecraft on top of the launch vehicle out to the launch pad, and that's where it sits tonight, awaiting its launch Wednesday. So on Wednesday, the team's going to be spread out across the globe. We're going to have a team, NASA will have a team at the Char launch facility observing and supporting the launch. We'll also have a team of about 20 folks at ISRO's ISTRAC, their mission operations facility in Bangalore. In addition to that, at JPL's mission operations facility, we'll have staff there ready to support the launch once the separation from the launch vehicle occurs. Okay, so launch is exciting. But what happens after launch and the milestones that we have in the weeks following launch are very exciting. I'm going to walk you through some of those. We have about a 90-day commissioning period, at which point we'll calibrate the instruments, we'll deploy, and I'll show you some of that right now. Some of the key milestones immediately after launch is that separation from the spacecraft will occur about 20 minutes after liftoff. And then we'll get what we call an acquisition of a signal from the spacecraft, and that will occur pretty much about the same time, about 20 minutes. And what you're watching right now is the solar arrays being deployed, and now we're going to start deploying the boom for the reflector. This is the first joint, and this will happen about 10 days after launch. This deployment will go on for about 8 days, and then it'll be complete. And so what you're watching right now is a 9-meter, roughly 27-foot boom being deployed, and it's going through its final hinge deployment right now. And what you're going to see in a minute here is the reflector start its bloom, what we call the bloom, or its deployment. That was based on its stored energy, and now you're going to see it being reeled in with some spooler motors that we have on. At this point, NISAR is ready to start collecting science, and we will continue to calibrate the instruments at this point, pop up to our science orbit, and begin collecting science. Let me reflect, now that you understand where the spacecraft status is, let me cue up the animation, please, showing the buildup of NISAR. I'd like to reflect back on the build. We've been at this over a decade with our partner ISRO, and it's been a phenomenal journey. As Karen mentioned, this is a large-scale partnership between ISRO and NASA, and a first of its kind. And as Karen mentioned, both the amount that we have learned from each other during this period has just been phenomenal. Both teams are in a rhythm now. During the height of COVID, we had about 65 engineers come out from ISRO and visit JPL and work to keep the integration and test going. And over the last 2.5 years, NASA has sent out over 175 engineers to ISRO's facilities to keep the integration and test going and get us ready for where we stand today and ready for launch. Both teams are eagerly awaiting and anticipating getting into this very busy sequence that I just showed you of the activities post-launch. But more importantly, and I think even beyond the folks that have worked and contributed to NISAR, is the scientists and people around the globe that are going to benefit from this transformative science. And that is really the exciting part. So when I think about today, a couple days before launch, what's going through my mind, it's been a wonderful journey. We've had a wonderful partnership, both within NASA and with our partner ISRO, of course. I'm anticipating a lot of very happy people, not only in the US, but in India, not only those of us, again, that have contributed, but also the rest of the world that is going to benefit from this science that NISAR is going to produce. And to tell you a little bit more about that science, I'm going to turn it over to Marco.
Thank you, Phil. It's very exciting to be here so close to launch. So we've just heard about all the amazing things that NISAR will do, and I'd like to go a little bit more into the details about the radar operations, how the radar works, and what the data will actually look like in practice. So NISAR carries two powerful radar systems. They're operated two different wavelengths, and together they will give a comprehensive vision of the land and ice-covered surfaces in all weather conditions, day and night. So we heard that NISAR will revisit the same location about once a week, but it also delivers unprecedented details, so very high-resolution imagery. And in the first animation, if we can cue it, I'll show you how that is achieved. So NISAR uses a technique called synthetic aperture radar, or SAR. As it flies along its orbit, NISAR basically sends out thousands of harmless radar pulses every second. These cover a very wide swath on the ground, hundreds of miles across. These pulses basically bounce off the Earth's surface and return signals that carry information about structure and conditions. And that's what is used by the scientists to understand how the surface changes over time. Now, these initial radar returns on their own are blurry. You can see actually an example in the upper right corner of that animation. But NISAR combines them to generate an image as if it was taken by a much larger antenna, one that would be miles wide if it existed in practice, physically. And this is why it's called synthetic aperture radar. We essentially synthesize a larger antenna in space to achieve high resolution from the motion of the satellite. By doing this, we obtain a sharp, high-resolution image from very, very far above the surface, 750 kilometers above the Earth's surface. And of course, the more pulses you integrate, the sharper the image gets, as you can see again in the upper right corner of the animation. In the second animation, we see what NISAR can do even further. So this is where things become interesting, in my opinion. NISAR can measure how the surface changes over time, so basically in 3 dimensions. In this animation, you're seeing California's Central Valley sinking several feet per year in some areas. And that is due to the groundwater pumping. So NISAR captures this motion using a technique called radar interferometry, which basically compares radar images taken at different times. In the case of NISAR, it's about 12 days. And that is sort of like using radar as a high-precision yardstick from space. Now, in the next image, if you can load it, we see what an interferogram looks like. So you see dark black areas, that's water, and you see colored stripes. These stripes indicate where and by how much the ground has moved. Where stripes are close to each other, that means that the ground has moved by a larger amount. And this is, in this particular case, a consequence of the volcanic activity. The volcano is actually in the center of the image, in the tip of that leaf-shaped pattern that you see in the image. This is called radar interferometry technique. In the next image, you see a different technique called radar polarimetry that has to do with the orientation of the electromagnetic waves. So radar polarimetry is implemented by NISAR. It's very useful for studying the structure of the land cover that we're seeing. In this particular case, we're imaging with an airborne instrument the Amazon forest. Again, black is water, a river running across the image. Green is intact forest, so that's the canopy that is penetrated by the radar waves, and reddish color reveals the water under the vegetation. This is an example of how the penetration capability of the radar are really important for understanding what is going on the surface. This cannot be achieved by looking at at optical images on the left-hand side, where you basically see clouds. In fact, optical images do not penetrate clouds and forest cover. And this is probably one of the things that most excites me about NISAR, the combination of radar interferometry and polarimetry to study how ecosystems change. We just published a paper, a method to estimate tree height from interferometric and polarimetric images, and we're really excited to look at how that method applies to NISAR data and reveals about our changing forests. This is only one example of what NISAR can do. There will be much more, and we're really eager to put our hand on the data. Back to you, Veronica.
All right, thank you to our panelists, and we're going to go to questions now. We've got several good ones coming in from social media, so I will start with those. Again, if you are, for listeners who want to submit a question via social media, you can do so by using the Ask NISAR, Ask N-I-S-A-R hashtag. And for members of the media on the phone line, if you want to ask a question, please press *1, and you'll be put into the queue. Coming from a question from Manish Mishra on YouTube, asks, NISAR is being called the most advanced radar system ever launched by NASA or ISRO. What specific breakthroughs in radar technology does NISAR represent compared to previous missions? And I'll let any of you in the room go ahead and answer that.
Yeah, this is Mark. I can take it. NISAR has 2 radar wavelengths, so that is definitely an important feature, and it's a breakthrough. We're using a reflector, an antenna reflector, that itself is also a technology innovation. But for the science, which is really something I work on, that reflector allows us to implement a technique called SweepSAR, which gives very high resolution. And that itself is really a breakthrough in the radar technology. In fact, we know that there are upcoming missions, missions that are in development, that will implement a similar technique. So in that regard, NISAR will be a first of its kind mission to implement that that high resolution capability with a new sweep star technique.
All right, thank you.
As actually our other panelists are pointing out, it's a combination of global and high resolution and global mapping. That's actually the key. Yes, that will be done by NISAR.
Okay, thanks. We're going to go to the phone line next, and we have Kenneth Chang from the New York Times. Go ahead.
Hi, thank you. This is for Karen St. Germain. You were saying that part of the power of NISAR comes from the fleet of Earth-observing satellites that you have. And in that nice animation you have, the administration is proposing canceling at least 4 of those. So I was wondering how much is that going to affect your abilities if Terra, Aqua, Aura, OCO2, and OCO3 are turned off. And I also had a question for Phil Barela. There was an issue with the antenna last year where it had to be sent back to JPL. Could you just recap what the issue was and how you fixed it and how confident that it's going to work as designed? Thank you.
All right, this is Karen. I will take the first question. So, the animation you saw is a snapshot of the fleet today. Over time, it is very much the case that some satellites retire, new ones come on. And I should also mention, this is only showing the NASA fleet. We also combine data with data from other international partners around the world. So what we're looking to do is exploit all of the data that we have access to at any given time, and in any snapshot in time, that available data will be different, on one day as compared to, years later. With regard to Aqua, Terra, and Aura specifically, those missions are approaching the end of their life. They're already in drifting orbits. So the science we're able to do with them is already changing as compared to the first 20 years. And actually, I really celebrate what those missions have been able to accomplish over more than 20 years of service. But that's changing as they reach the end of life. We will combine NASA data with a wide variety of data of all different types, of all different measurement techniques. Take over to Phil.
Yeah. Hi, this is Phil Barela to your second question. So the reflector, as you point out, was found to have some concern on our part for its optical properties. And this would have resulted in potentially the reflector bonded joints and other components of part of the reflector getting too warm. And so we did send it back to Southern California, and we changed those optical properties very methodically. We walked through the entire reflector and made sure we had plenty of robust margins on everything else, and then we shipped it back integrated, and you saw it there in the photo about to be encapsulated. So we're ready to fly.
Okay, we're going to take our next question from Jeff Faust of Space News. Go ahead, Jeff.
Good afternoon. Question for the NASA part of the NISAR team. Curious, beyond sort of the obvious obstacles like distance and time zones, what sort of challenges you had working with ISRO on NISAR, but also maybe some unexpected benefits of the cooperation to enable the spacecraft to finally make it to the launch pad? Thank you.
Wow, it's a long list. As I mentioned in my summary, I think we've acknowledged both teams. We've just learned so much from each other, and this is the first time, as I mentioned, we've worked this intimately, where they spent years at our facility and us now years at their facility. So it's a very long list. Really some wonderful examples. I won't get into details here, but the way they solve problems, the way they approach a problem, is somewhat different depending on the area than we do. And so we really observe that, and I think there's a lot of benefits, there's a lot of lessons we can take back. And we've heard them say the same thing about us. Some of the ways we do business are very different from them. They're taking that back, looking at it. The challenges was really getting used to those differences and appreciating them. And the teams, I think, really, to their credit, remained with open minds, and we got into this rhythm at the end, as I mentioned, that it is a extremely powerful team at this point, and wouldn't trade it for the world.
All right, thanks, Phil. We're going to go to our next question from Bruce Einhorn from Bloomberg News.
Hi, everyone. This is a question for the whole team. Could you provide info on the cost of the project? A lot of the media reports have said that the price tag is an estimated $1.5 billion. Is that correct? And if not, what is the right number? And also, is it possible to say what percentage is from NASA, what percentage is from ISRO?
Karen, would you like to take that? And I don't know if we have the graphic available that shows the contributions from the two countries. But go ahead, Karen.
Yeah, if we've got that graphic, it'd be great to show it. So the NASA contribution over the expected primary life of the mission is about 1.2 billion. When it comes to the ISRO costs, what I would say there is ISRO has a different business model, a different way of accounting for costs and so forth. So it's really difficult. It would be difficult for me to draw a comparison or conclusions based on the money. So I think the more informative way to actually talk about the contributions of our two countries is actually shown in the graphic here, where you can see that there were very equitable contributions by NASA and ISRO. I walked through them earlier, but the deployable, that large deployable, it's almost a 40-foot antenna, almost 40 foot in diameter antenna, and the boom that supports it, and all of those mechanisms, and the L-band SAR, as well as a variety of other smaller components were delivered by NASA. And then, of course, on the ISRO side, the S-band radar is the other part of the instrumentation, and then all of the supporting functions, the spacecraft bus, the solar arrays, and the launch and operations. So equitable and completely joint and integrated mission. Yeah, that's, I think. Oh, Gerald, you want to add something?
Yeah, this is Gerald. We talked about cost of the mission, but we've never talked about what is that buying, I'll say, the world. NISAR, as I described, is basically collecting more data than any other NASA mission ever to planet Earth, and by a large amount, again, 3 times the volume than what was collected in the solar system. And so with that, we're going, imagine being able to go ahead and collect data, I'll say 5 meters by 6 meters. So we're looking at 5 yards by 6 yards, or a little bit yards, on every square section of Earth twice every 12 days. That is a lot of data. Actually, if you start looking at what the cost of that data is, just over 3 years, it's going to only cost about 2 cents per square kilometer, per square mile for that data. No other mission has actually that cheap of data. We're able to go ahead and do science actually very economically. We're able to do science that was not possible without this. Yes, the upfront costs are high, but the scientific dividend and the scientific costs per square mile is cheaper than anything else that's out there. So it's amazing that we're able to do that actually on this mission that only costs this much.
All right, we'll move on to the next question. That will be from Gurbir Singh, an author based in the UK.
Thank you very much. Can I start by saying, acknowledging all the hard work that you guys at NASA and your colleagues in Israel have put into the NISAR mission. The data in return will be really something and consequential. My question is about the data download. The press kit says that all S-band and L-band data will be available to Indian government users through Israel's National Remote Sensing Center. So does that mean that the S-band data will not be available publicly from Israel's National Remote Sensing Center as NASA's L-band data will be?
This is Gerald. I'll go ahead and work with that. All the data from NISAR, this is the L-band data that NASA is collecting, that will be available through the Alaska Satellite Facility for no charge. All of ISRO's S-band data will also be available through their Buhindi system, and potentially get a link up in the chat at some point. ISRO is actually providing the data free and open. We actually had a meeting today where they were going over exactly what they are providing, and it's going to be a wonderful data set. So where is ISRO collecting the SR data? It's not quite global. Most of the data is actually being collected over India, and then we have parts in the United States, mostly the western United States, and then we have some different sites around the world. We've got the Congo in Africa, we've got the Amazon rainforest, we've got some glaciers, but more importantly, we're also imaging all of Antarctica, Greenland, and I'll say some of the northern sea ice north of Alaska, where they're collecting data in both the L-band and S-band. Actually, whenever S-band data is being collected, we're also collecting the L-band data. And so this can be a very rich data source that's free and open there. But with ISRO, you've got to go ahead and go to their system, their NRSC, National Remote Sensing Center, to their system there. You've got to log in, create an account, and then you'll have the same access that everyone else will have there.
All right. Our next question comes from Alexandra Whitsey from Nature Magazine. Go ahead, Alexandra.
Hi, thanks for taking my question. This is for Karen St. Germain. I want to follow up a bit on Ken's earlier question about kind of future missions and the way the future of NASA Earth Science Fleet might look. So you talked about missions that are sort of end of life and maybe will be turned off soon, but NISAR is also supposed to be the trailblazer for Earth System Observatory future missions meeting decadal survey priorities from the community. And NASA's budget request would not, for next year, would not continue formulation of any of those future Earth System Observatory missions. So what's lost if we have, this great mission like NISAR we're hearing about today, if we don't get to have big future missions like that following it?
Yeah, thanks for the question. The budget process is playing out, and our commitment, our passion is to do the most advanced science we can do with the budget we're allocated. So once we have clarity, we will move forward with planning for the future missions, and we are, of course, hoping for a very nice long life for NISAR and some of our other missions that we recently launched that are likewise breakthrough missions. I'm thinking of principally SWAT and PACE. So we think that we are actually entering a pretty rich golden age of new types of data that can answer questions we've never been able to answer before. And we will look forward to moving out on building the future missions once we have a little more clarity on the direction from Congress and the administration.
Okay, I'm going to give you a question from WXTIS on YouTube. What are the challenges of managing NISAR's high data rate from dual frequency, large swath imaging And how does the ground segment ensure timely data delivery?
This is Phil Barela. It is a challenge. 37 terabits per day, daily downlink volume, and then that's unprocessed. Once we process it, it becomes even more voluminous. So there's really only one way to transfer effectively that type of data. We have 4 ground stations, 4 NASA ground stations being used for the L-band. We have 2 ground stations being used for the S-band radar. So each pass, they will downlink their allotted amount of data to those stations. Those stations integrate it, and then they send it to the cloud. And so post-processed, that information that's sent to the cloud would be in the repositories that Gerald described and available for everybody. So obviously I've glossed over all the details that went into the years of developing this system, but it is a challenge. The challenge has now been fully tested. The ground stations are certified, ready for launch, and ready to start processing the science data.
And, this is Gerald, if you don't mind if I add on to that. The sheer volume of data that NISAR is collecting is actually pushed NASA into managing data in the cloud. And so given the sheer volume of data that I described earlier on, there was actually not enough data bandwidth between Southern California and Alaska at the time that we were looking at this to actually process the data and move it up to Alaska where we actually have our archive. And so the solution that made the most sense was actually moving into the cloud. And since that, we have moved everything into the cloud. And what's wonderful with that is now we could actually start developing tools where the tools reside next to the data. And anyone from around the world, you could pick up your favorite phone, iPhone, iPad, Galaxy, what have you, and be able to go in and actually process data where you are and when you want to. Because of these data challenges that we have, these are some of the wonderful benefits that have come out of the challenges that we faced with NISAR. So Phil described how much data is being downlinked. That, once we process it, turns up to about 85 terabytes of data per day and petabytes of data every year. So it's a huge data piece, and we've actually come up with a solution that is actually pretty seamless between what Phil described, downlinking the data at all these new sites, and having it all accessible to anyone and everyone around the world.
All right, I'm going to go to another question here from YouTube. A couple people have asked, are there any plans for more joint missions between ISRO and NASA? Karen, do you want to answer that?
Yeah, so we don't at the moment have any, have future plans. We have been so focused on getting NISAR completed and into orbit and beginning to extract the incredible science and applications out of the mission. So we don't have another mission lined up at the moment, but I assume we'll start talking about common interests on next missions at some point in the near future.
Okay, and we'll make this our last question today. Large Mamal on YouTube asks, I get the idea behind radar, but can synthetic aperture radar be explained for a layperson? Phil, is that something you might be able to take?
What was the question again?
Or, well, any of you. Is there a simple way to explain synthetic aperture radar?
I can try, and perhaps Gerald can complement. Yes, so a synthetic aperture radar, the word synthetic means that we are essentially working as if, the radar is working as if we have a very, very large antenna in space. Of course, we cannot send in space a very large antenna. Several kilometers away we would like to have, several kilometers large antenna we would like to have in space. We cannot launch it. And so what we do, we send out pulses, and then we combine these pulses from different locations as the radar flies along its orbit. So it's essentially just like faking it in a way, by just looking at the Earth from different angular positions as the satellites flies along its orbit. So just to say in a very simple word, we're sort of leveraging the fact that the satellite moves, and as it moves, it creates artificially a very long antenna, and that is basically what gives you a very fine resolution in space. But of course, the physical antenna is much smaller.
Yeah, that was the point I was going to amplify. This is Karen. That the thing that we're really going after is very high spatial resolution on the ground. And one of the basic laws of physics is to sample a very small area on the ground, you need a very large antenna. And of course, we're trying to get to centimeter scale change at what, 10, what did we say, 10 foot resolution? 10 foot resolution. We would need, as Marco said earlier, a miles large antenna to do that in a traditional way. So yeah, as Marco said, instead of having one big antenna, we essentially take a small antenna and move it. And through processing, we simulate what we would get, or we through data processing analysis, we can recreate what we would have seen with that miles-long antenna. Does that help? Go ahead, Gerald.
I'm going to add on here, but I'm going to go a completely different way.
Of course you are.
Of course. Most people are used to looking at the ground, I'll say just like it's a photograph. So these are Landsats. Effectively, you take your favorite smartphone, you put it in space, you take a picture, and you've got an image of what's on the ground. And so that's what most people are used to. With radar, your camera actually has a flash. So it's completely dark. You send out a flash, you illuminate the ground. And if that flash keeps on going off enough as you're moving around the Earth, you're able to start seeing the Earth come together. One of the things that's unique about radar is if you think of, I'll say, a policeman or a policewoman that actually has a radar gun. They shoot. What they do is they're actually pointing a radar gun at a car, and the radar signal goes from the radar gun out to the car and comes back. Well, it actually does that, and then the car moves a little bit further, and it sends another pulse out and another pulse out. We are able to, with the radar, measure how fast that car is moving. For what we're using with synthetic aperture radar, instead of having the car move and the radar gun fix, we're actually looking at the ground that's staying the same, and the radar is moving in space. So we are able to actually measure very small changes. We're talking millimeter scale changes of the Earth's surface using the same type of technology that the police use in their radar gun, but we've got to mount it in the satellite. And the fact that we're sending out all these pulses, kind of like the flash bulb that I was just talking about with the camera, we're able to create these images. And the fact that we have this large antenna, that's one of the beautiful things with NISAR. Why do astronomers want bigger telescopes? Bigger telescopes collect more data. And so NISAR has the largest radar reflector ever launched into orbit, and it's because when our radar pulses leave the satellite, goes down to the ground, comes back in, we're collecting more data that's ever been collected from a single radar pulse. We're able to focus it and see things more sensitive on the ground than we've ever been able to do in the past. That's been some of the magic of NISAR, and we'll be able to do science and applications that we've not been able to do because we have this incredible radar. It's using these advanced techniques like SweepSAR, this large radar dish. We've got all these different downlink stations, and we have a complete support network working with India, working with all of our other agencies to actually bring this stuff to you. So we're looking forward to what NISAR is going to be able to go ahead and provide to the community, supporting the science, the application. And I don't know how many unknown users are on the phone right now. I'm hoping that people will be inspired to take a look at NISAR data, go up to the Alaska Satellite Facility, ASF, download some data. Once NISAR launches, you're going to see things that you never knew were there. Go NISAR.
All right, thanks to everyone for answering that question. Thank you again to all the panelists and those of you who are on the line and on YouTube. We hope you'll all join us for the NISAR launch coverage on Wednesday. Mission commentary will begin at 7 a.m. Eastern, 4 a.m. Pacific time. Our broadcast will originate from here at JPL, and we will switch to the ISRO live feed at around 7:40 a.m. Eastern, and we will remain with them all the way through launch. Launch, I misspoke earlier, launch will actually be at 8:10 a.m. Eastern Time, 5:10 a.m. Pacific, and if you are in India, that launch time is 5:40 p.m. You'll be able to watch the launch commentary on NASA Plus and also the NASA flagship YouTube channel. That's youtube.com/NASA. For more information on the mission, please NASA.gov/NISAR. You can also follow along on social media on the NASA JPL social channels, NASA Earth, and at NASA. And you can find the NISAR launch press kit, which is loaded with great information, at go.nasa.gov/NISAR press kit. For media and others who are looking for the source images and videos that we showed during this teleconference, you'll find links to those in the YouTube, NASA JPL YouTube channel where we have live streamed this briefing. They will be in that description. Thank you again, everyone, for joining us, and go NISAR.